Hello, I'm Rhoda. Let's solve the KKT question. So first we can say this is a minimization problem, and the objective function is continuous, and those three constraints be compact, so we can always find a global minimum under the KKT condition for this question. First, we need to rearrange the inequivalent constraint. We need to let them become less or equal to 0. So we can find G1 to G3, and then we need to form the Lagrangian. This is the most important part when you want to start a KKT question. Because this is a minimization problem, so this part of the Lagrangian will be plus. This is our Lagrangian function. And then we need to find the KKT stationary condition. We need to take the partial derivative of x and the partial derivative of y. And also in this step, I pre-processing some equation. I take the second derivative and also find the gradient of the inequivalent constraint. They can help me to more smoothly to constrain the border Hessian in the following step. Those 11 equation is pretty important because they call the KKT condition. If you find a point that not satisfy this 11 equation, it means this point is not feasible. We will not discuss it. If it's satisfied, we can go to the next step to test its local maximum or local minimum. And also for this graph, we can find some point of its local maximum or local minimum. This is also shows we have the solution for this question. So the logic of the KKT question is just step 1, discuss for each cases and find the potential point. Then to test is satisfy KKT condition or not. If not, it's not feasible. If yes, go to step 3, but to be the border Hessian and to test use the leading principal manner. If it's negative definite, the shape is like this. So we have the local maximum. If it's positive definite, it's shaped like this. We have this local minimum. And step 5, just sub them into the objective function to find the global minimum. Because we have the 3 constraints, so we have 8 cases need to discuss. For case 1, no constraint is bounded. We can find the point, but we only use the Hessian matrix because you only use the border Hessian when we have the constraints be bounded. So we can find its negative definite as local maximum. For the case 2 to case 4, we only have 1 constraint is bounded. So we can find the border Hessian and use the border Hessian to determine it's the local maximum or local minimum. So for this part, we can find the potential point, put them into the border Hessian to test the determinant of the border Hessian. It's positive definite, it's local minimum, it's what we want, it's great. And then for the following step, we can find point, but it's local maximum, we don't want it. And then to another point, it's also the local maximum. And case 3, it's also we can find the potential point and substitute them into the border Hessian. We can find it's also the local maximum. And another cases is also be local maximum. And case 4 is similar. We just find the point and the border Hessian told us it's also the local maximum because it's negative definite. For the case 5 to case 7, we have 2 variables and 2 constraints will be active. In this kind of situation, we cannot find the second order condition, so we cannot find the border Hessian. We cannot use the border Hessian to test its local maximum or local minimum. It's just a point. It may be local maximum. It can also be local minimum. So we just go to step 5 to test its be global maximum or global minimum. So this part is in conclusion. First, we should test the point is satisfied, but no conclusion. Also, this part, we can say it's not satisfied the KKT condition, so it's not feasible. We not discuss it. This part is satisfied. We'll discuss it in the step 5. And the case 7, also discuss in the step 5. And this case, also not satisfied. It's not feasible. We will not discuss it. For the case 8, we only have 2 variables, but 3 constraints will be active. This means we will know solution for this case because this is overdeterminant system with inconsistent equation. So the case 8 is not feasible. Those are the points that I can observe or calculate from this question. And those 4 are the global minimum point, and the global minimum value of this question is -2. Thank you for watching.